Yes, questions. Your last chances before the exam to ask questions. Your last chances, plural. You have 5 days. Oh, yeah, why not? When had we done on Friday? So, are you free on Friday? Okay, I will be in my office probably throughout the day. But let's fix a date, also an hour, a problem-solving hour. All together or office hour? All together. Okay, I think last time we did it on Wednesday, you know? Friday was the office hour. Oh, no. Just before the exam on Friday. Okay, so at what time? 12:40? Too early? Okay, 2:40? No. At 3 I need to leave. Let's do it 12:40. You show up late. So problem-solving hour. Okay, on Friday at 12:40, I will check for a suitable classroom, and then we can meet. Well, depends on you, depends on the classroom. Okay, so last Friday, if you remember, we were discussing the sources of magnetic field. And one source of magnetic field is the current carrying wire. And so if you have a current carrying wire, let's say the current is running in this direction, and what do you expect the direction of the magnetic field to be at this point? Well, right-hand rule, thumb in the direction of the current, your fingers in the direction of the magnetic field. So more or less the magnetic field lines will circle around the wire in this sense. So at the bottom it will go into the screen, at the top it will be out of the screen. So whenever you are asked for a vector quantity, don't forget to show its direction. And now we said that, okay, so this is the direction, but how can we calculate it? One means of calculating the magnetic field was the Ampere's law. So if you take any region of space, you just take a loop, and at every point along this loop, take an arbitrary loop, you divide this loop into very small segments. You have to choose a direction for your loop. Let's say this is the direction of the loop, dl. And inside there might be some currents inside. Let's see, I1 going out, I2 going in, and I3 outside. Well, you have some arbitrary currents. You choose an arbitrary loop, and then if you calculate just divide it into segments. At every segment, you define this very small vector dl along your loop, At that point, you calculate the magnetic field, take the scalar product with this vector, and repeat this for all the segments and sum them up. You get this integral, and that integral is always equal to mu0 times the enclosed current. And in this particular example on the screen, if we just take B dot dl, this will be mu0. What is the enclosed current in this case? I what? Well, this is 1. Okay, this is 1, this is 2, this is 3. So it's I1 minus I3, I2. Well, how you again curl your fingers along your loop. No. Then your thumb points the positive direction of the current. So if the current comes from behind this area and comes to the front, then that is a positive current. If it goes in the opposite direction, it's a negative current. So that is why I1 is positive, I2 is negative, and I3, although I3 contributes to the magnetic field at every point, when you take this integral, the integral is 0. The integral only depends on I1 and I2. And then we did several applications of this. We applied it to the infinite wire. Then we had the solenoid, which was essentially a cylinder. And you wrap a wire around the cylinder. And in this example, we chose such a loop. What we did, just like in the Gauss law, we first said that in such a system, if this is infinitely long, the magnetic field inside should be, magnetic field lines should be straight along the parallel to the axis. So we chose such a loop such that we get contributions from this segment to B dot dl, but no contributions from the other segments. And we had shown that the magnetic field of the solenoid, inside the solenoid, is uniform, mu0 I n, n being the number of turns per unit length. This and in the wire there is a current I. What is the direction of the magnetic field? Towards the left or towards the right? Well, you can, if you like, you can just take one of the wires, your thumb in the direction of the current, then your finger inside the solenoid, the magnetic field will be towards your right. Or if you like, just wrap your fingers in the direction of the current, your thumb points in the direction of the magnetic field. So B is pointing in this direction. This is the direction of B. And then we looked at the problem of the toroid, which is just a donut-shaped object, where again you just wrap coils around it. Ideally, infinitely many of them. Let's say the current is running in this direction, well, around this torus. What will be, and if you look at just from the top, this is what you will see. Let's say the current is into the screen on the outer edge and out of the screen in the inner edge. What will be the direction of the magnetic field in this case? Clockwise, counterclockwise? Clockwise or counterclockwise? Well, your thumb along any wire, then your fingers, your other fingers, will just show you the direction of the magnetic field. Or from here, if you like. So the magnetic field will look like this. Magnetic field lines. They will be just circles. So this is not B, that is I. And the magnitude of the magnetic field in this case just turned out to be mu0 over 2 pi r times I times n at this point. This is the distance r. Here n is the total number of turns. And here n is the number of turns per unit length. No, I mean, we are not using this one to obtain this one. We just use the Ampere's law straight away. So you see in the... No, we did. Well, how did we use this? We just chose a loop. Let's say, let's choose this loop. In this sense. So dl is, let's say, this segment over here. So b dot dl, along that loop, b and dl are always in the same direction. This is b times dl. B is a constant. That is the first thing we should show, because along this line, r is constant, and we first argued that b can depend on r and also z. Along this loop, both r and z are constant. So b is a constant around this blue loop. So I can take it out. And what remained was just the magnitude of the magnetic field times 2 pi r, which has to be equal to mu0 times I enclosed. This time we have n loops, n wires inside my loop, and each one of them carries a current I. So this gave us B is equal to mu0 over 2 pi r times I times n. You see, that one and this one, by the way, they are not very different. You see, n is the total number of loops. 2 pi r is this circumference. So especially if this toroid is huge, but the cross-section is very small, r will be more or less constant, because the inner radius and the outer radius, they have more or less the same value. So this will be n over the circumference of this toroid. Well, but that is nothing but the number of turns per unit length. That is this expression over there. I don't remember the other n. Well, this is just the number of turns. How many turns does it make? ED times VD times E times N. This N. But this was the number density of the charge carriers. This is different than what we have over here. You see, here we define N to be the number of turns per unit length. You see, the number of characters in the alphabet is quite limited. And, well, we use the Latin alphabet, Greek alphabet, but still we have hundreds of different quantities to name. So they overlap. Other questions? Okay, now, if you remember when we were discussing the Gauss's law, we said that the Gauss's law is always valid, but it is not always useful in obtaining the electric field. Now, similarly, Ampere's law is always valid. Whatever your system is, it is always valid, whatever the currents you have in your system. But still, its use in obtaining the magnetic field is limited. Because if we don't have any symmetry in the problem, you see, in these problems, we already knew before using the Ampere's law that B can depend on the radius and the z-coordinate only. It cannot depend on the angle, and it has to be along this direction. So we knew it beforehand, before using Ampere's law. Similarly, in the case of the solenoid, we knew beforehand that the magnetic field line should be parallel. So that is, the B can only depend on the distance from this axis, and well, that's it. It cannot depend on the z-coordinate. It cannot depend on the angle around the central axis. So without that knowledge, we couldn't calculate the magnetic field using the Ampere's law. So what do we do if we have a problem that doesn't have this symmetry? Then we have the Biot-Savart law. Now what it states is, let's assume you have an arbitrary wire, not necessarily straight, not necessarily a solenoid, not necessarily a toroid. It creates a magnetic field, and the magnetic field that this wire creates, in fact, can be divided into very small contributions coming from different segments. Let's say it carries a current I. Now let's just take one of these segments over there. Let us take this segment over here. Here. Again, we will define this vector dl. Well, dl, the magnitude of dl is the length of that segment, and the direction is along the wire in the direction of the current. And now we can look for the magnetic field at this point, P. Now, the magnetic at this point will receive contributions from all these segments, but the contribution from that dl can be written in a simple form. Let's call this vector r. So I have this dl vector, dl segment. P is the position of that point, r is the position of this point P relative to that segment dl. Then the contribution from dl to the magnetic field at the P is mu0 over 2 pi I dl cross r over r. Now let me just show the r hat cross over r squared. Or if you like, mu0 over 2 pi I dl cross r over r cubed. Yes. Where? This is r squared. Well, you see, here this is the unit vector. This is the radius, this whole vector, not the unit vector. Well, that is what I am checking for. Okay, it is 4 pi. Which one? Well, because mu0 is 4 pi times 10 to the power minus 7 Tesla meters per ampere, meter square per ampere. Well, you see, this is the way we define it. What we measure is that this coefficient over here should be 10 to the power minus 7. Now, of course, does it agree with what we had said before? We already have studied the magnetic field created by an infinite wire. Okay, this is our claim that the magnetic field created by this very small segment is given by that expression. But can we derive the magnetic field created by an infinite wire starting from here? By the way, what will be the direction of this dl cross r? In which direction? How do you calculate the direct outside? Yes, you see. This is dl. Your forefingers in the direction of the first vector, your palm in the direction of the second vector, your thumb is the cross product. So it's outside. Well, we already knew that if we have such an infinite wire, the magnetic field lines should go somewhat like this. So the contribution from this segment is outside, just like the magnetic field is. Now let's calculate, let's apply this. The magnetic field of an infinite wire. We already know the result. So we know that B should be equal to mu0 I over 2 pi r. But let's try to drive it. This is our infinite wire. It carries the current I. So let us first divide this into very small segments. Pick one of them. Let's calculate the magnetic field at this point over here. Let's pick one of the segments and write down its contribution. Let me pick that segment, dl. This is the r vector. Now, what is the direction of the magnetic field created by this? The expression is over here. It's in the direction of dl cross r. It is outward. If I choose this segment, what will be its direction? This segment? Well, all of these segments will contribute in the outward direction. They will all point in the same direction. So it's enough to calculate the sum of the magnitudes. All of them is pointing in the same direction. So when I sum all the contributions to the magnetic field, I will be basically summing the magnitudes, and the resultant vector will be pointing in this direction. So let me write the magnitude. Well, Biot-Savart law tells me that there is this overall coefficient, mu0 over 4 pi. Then we have, let me write it over here, mu0 over 4 pi I dl cross r, let's say r unit vector over r squared. Mu0 over 4 pi times I. What is the magnitude of dl cross r hat? This is the unit vector in the direction of r. The product of the magnitudes, dl times 1 times sine of the angle between those two vectors, sine theta, where this angle I called theta, divided by r squared. This is the contribution to the magnetic field from this very small segment. So the total magnetic field will be just the sum of these dBs, which will be mu 0 over 4 pi I, the integral of dl sine theta over r squared. Now, as I go from segment to segment, does sine theta change? It does change. Does mu 0 change? No. 4 pi doesn't change, I doesn't change, but theta changes from segment to segment, r changes from segment to segment. Now let's evaluate this. Well, of course, we first have to express everything in terms of the same quantity. So let us choose an origin. Let's say this is my origin. Let's assume this, let's call that, let's call that capital R. That is the distance of that point from the wire. Now, what is this small r? Well, capital R over small r is just sine theta, which tells us that small r is just capital R over sine theta. So this allows me to relate one of these variables to sine theta. Now, I will be expressing everything in terms of theta. Now, dl is basically dx. If this is the x-axis, it is how much the x-coordinate changes as we go from one segment to the other segment. Now, what is x over r? I will say minus cosine theta. Or if you like, let me put the minus sign on the other side. Minus x over r is cosine theta. Remember, I'm looking at this point. At this point, x is negative. So minus x is this length. That's why I have that minus sign. X is the coordinate. It can be positive or negative. Minus x, at that point, minus x is positive. So x over cosine theta is a positive number, which tells me that theta is somewhere between 0 and 90 degrees. If I were looking at some segment over here, x would be positive. If x is positive, minus x is negative. Minus x over r would be negative. That would tell me that cosine theta is negative, which will tell me that the theta angle is larger than pi over 2. Well, that makes sense. If we are looking at this dl, theta over 2 is the angle between this vector and this vector. It's larger than 90 degrees. So at least the signs make sense with that minus. So my x is equal to minus r times cosine theta, or minus capital R cosine theta over sine theta. So we can calculate dx. If you just take the derivatives, dx will be r over sine squared theta d theta. The derivative of cotangent is minus 1 over sine squared. Now we have everything expressed in terms of theta. This was dl, remember. So now let's express b in terms of an integral over theta. It's mu 0 over 4 pi I. Well, dl is d theta r over sine squared theta. This is dl. Then I have sine theta. Then I have 1 over r squared, which is sine squared theta over r squared. What is the range of theta? It's 0 to pi. Because I start from that segment over there at that infinity. The further away I go, the smaller the theta becomes, so I start from theta is equal to 0. And then I go eventually to that angle over there, to x is equal to plus infinity. And then my r vector is pointing in that direction, so my r vector gets larger and larger, and eventually it reaches pi radians. So that's why we go from 0 to pi. Well, let's do the cancellations. Let's cancel this one. So b is equal to mu 0 over 4 pi I from 0 to pi d theta sine theta over r, which is mu 0 over 4 pi I over r minus cosine theta. This is the integral of sine theta, theta from 0 to pi, which is mu 0 over 4 pi I over r minus 1 plus 1 mu 0 I over 2 pi r. This is RB. And the result does agree with our previous result that we had studied using Ampere's law. Well, you see, this number over here is known to be a constant. And we could have just as well defined this whole thing as some mu 0. We don't do that. The reason why we don't do that is, okay, it will simplify the Biot-Savart law, but then that 4 pi will appear in the Ampere's law. So we prefer to have a simpler Ampere's law. That's why we put that 4 pi over there. You see, actually in mu 0 there is this 4 pi. So they would just cancel actually. And in fact, this just allows you to calculate the magnetic field of a wire of an arbitrary shape. Other questions? Well, let's do a couple of more examples. Now this time let's assume a ring. Let's say we have this ring. It carries a current in this direction. So this is the center of the ring. And let's just imagine this straight line passing through the center of the ring, perpendicular to the radius of a given to the plane of the ring. And let's pick up this point over here. What is the magnetic field there? Well, this will be, in fact, very similar to the example we did when we were studying the electrostatics. So if you remember, in electrostatics, what we did was we looked at a segment over here which created an electric field in that direction. The symmetrical segment over here created an electric field in this direction along this line. And when we summed them up, they both created an electric field along this line. So the electric field was perpendicular to the plane of the ring. Well, we will have a similar effect over here. Let's start with a small segment at the top. Let's take this segment. This is my DL. Now, try to think of this as three-dimensional. This DL is, in fact, pointing towards you. So this is my DL. And R vector corresponding to this DL would be pointing in this direction. What will be the direction of the magnetic field created by this very small segment? DL is pointing towards you. This is my R vector. DL, your palm pointing in the direction of R, and your thumb is in the direction of B. B is pointing in this direction, so it will be pointing in this direction. So let me just draw this a straight line. So this will be the direction of dB. And this is 90 degrees. Do you agree with this direction, everyone?
O zaman yukarıdakine de aynı şey yapmamız lazım.
We did.
Ama dik çizmedik. Ara dik değildi.
Well, you see, in the top one, you see, in this one, DL is on the screen. So that was the direction of DL. This was the direction of R. So B was pointing in that direction.
Gene zaten R'ye dik oldu.
Yes. In this one, DL is not in the screen, in the plane of the screen. DL is pointing towards you. This is R, so it has to be perpendicular to this plane, that's for sure. And which perpendicular? Well, DL cross R, this perpendicular to that plane. At this point, this is your DL. This is the R vector, so it's perpendicular to both of them. Convinced? Do you agree with the directions?
Can you show the cross product in the first example?
This example, the wire example. You see, DL is that one. Then we have this R vector. So these are our two vectors that we need to take the cross product. DL, the first one, cross R, the second one. So how do you calculate the direction? Your forefingers in the direction of DL, your palm points in the direction of the second vector, so your thumb points in the direction of the cross product. So that's why we have the B is pointing outward at this point. Now at this point, in this example, this is my DL, this is my DR. Forefingers in the direction of the first vector, which is DL, your palm in the direction of the second vector, then your thumb is the direction of the cross product. Okay. And just always keep in mind, the cross product is always perpendicular to both of them. If this is your RR, this is the other vector, then here we have this plane. The cross product has to be perpendicular to both of them. Now let's look at the other segment on the symmetrically opposite side. Well, this time it will be pointing into the screen. You see, this is the sense of the current. The current is running in this sense, towards you, away from you. This is my ring. My ring is not on the screen. My ring is perpendicular towards you. This is how the current is running. At this point, it is coming towards you. At the bottom, it's going away from you. Now, this is my DL. This time, this is my R vector. It's pointing from here to there. DL cross R is pointing in this direction. So let me draw this straight line first. It should be perpendicular to this one. And dB would be pointing in this direction. This is again 90 degrees. Do you agree with the directions? Can you obtain them? No? This one. Well, first of all, DL, remember, this is the ring. The current is running like this. Towards you, down, away from you. Up, towards you, down, away from you, up. So at the bottom, my DL is pointing in this direction. This is the direction of DL. Then this is my second vector, the position of that point P relative to my DL. Now I have to take the cross product of these two vectors. This is my first vector, DL. This is my second vector. So how do we take the direction? How do we find the direction? 4 fingers in the direction of the first vector. Then you rotate your palm such that your palm points in the direction of the second vector. Then your thumb points in the direction of the cross product. So this is my first vector. This is the second vector. So this is the cross product. Now this angle over here, let's call that angle theta. What is this angle? Also theta. What about this angle? Pi over 2 minus theta. So is this angle. Pi over 2 minus theta. So you see, these two vectors make the same angle with the horizontal line. Well, let's write their magnitudes. This is mu 0 over 4 pi I times dl cross r hat over r squared. So we have to take the magnitudes. Let me give some names. Let's call this length L, this is r, and this is small r. Now what is the product magnitude of that cross product? Well, the product of the magnitudes, sine of the angle between the two. What is the sine of the angle between the two? What is the angle between those two vectors, dl and r? Well, let's look at this one. This is our dl. R is this vector over there. 90 degrees. This angle here is 90 degrees. Sine of 90 degrees is 1 divided by r squared. Now, the vector dB would be the magnitude times cosine pi over 2 minus theta. Let me give some names to the axis in the I direction, plus dB times sine pi over 2 minus theta in the j direction. But you see, since these two vectors, they have the same magnitude. They are pointing in, they make the same angle with the horizontal, but in opposite directions. When I add them, their vertical components will just cancel. This j components will just cancel. I will end up having only the I components when I sum them all up. So the magnetic field, the total magnetic field, will be the sum of only the horizontal components. Which is mu0 over 4 pi I dl over r squared. Well, this is just sine theta in the I direction. Well, what I did, I just wrote dB is the magnitude of that dB is, we had already calculated it. I wrote it over here. Cosine of pi over 2 minus theta is just sine of theta. Now let's see, as I go from segment to segment, you see, I have many segments along this ring. From this segment to that segment, from that segment to that segment, I'm just summing all the contributions. From segment to segment, does theta change? Theta doesn't change. You see, theta is the angle. You see, this is, let's say this is my horizontal axis. This is my horizontal axis. Ring is over here. My two arms are always making the same angle. So theta doesn't change from point to point. In this example, theta doesn't change. Well, mu0 and 4 pi are constant. I is constant. Does r change? Small r. Small r doesn't change. Capital R doesn't change. Nothing actually changes. So this is equal to mu0 is a constant I can take out. I is a constant I can take out. 1 over r squared is a constant I can take out. Sine theta is a constant, take out of the integral. I hat is a constant vector. Sum of dl just gives me 2 pi capital R. So this is the total B, total magnetic field created by the ring on a point on the axis passing through the center. Well, let me just simplify it a bit. Here there is a 2, which is mu0 I over 2 r squared, capital R. Now sine theta is capital R over small r. So this is mu0 over 2 pi, let's say I pi times r squared divided by r cubed. Well, the pi is cancelled, but I just inserted another pi. There's a pi over here, a pi over here. What is pi r squared, by the way? Area of the ring. Well, you see, the ring has an area pi r squared. It carries a current I. What is the product of the current times the area of a ring, of a loop? The magnetic dipole moment. So the magnetic field is mu0 over 2 pi times the magnetic dipole moment of the ring divided by r cubed in the I direction. Okay, any last questions? Well, let's see, does it make sense? If r is equal to 0, the magnetic field should be 0. Well, if L is equal to 0, should the magnetic field need to be 0? No. You see, at L is equal to 0, well, you see, that was the electric case, because the electric field was pointing away from the charges. This one, no. At this point, in fact, if you look at the center, all the contributions are pointing in this direction. So they don't give 0. This is different than the electric dipole case. Now, electric charge, ring of charge. Okay, see you on Thursday.